All right. Welcome, everyone. Welcome, people online. We're so happy to have Dr. Ziran Wang here today for a talk. Dr. Wang is a assistant professor at Purdue University. He is also the assistant director of Institute for Control Optimization and Networks at Purdue University. Dr. Wang, before joining Purdue, Dr. Wang has worked for Toyota Research and Development Institute, where he had a lot of research on cooperative driving automation. And right now, as you will say later, he start working also on large language models. So without further ado, Dr. Wang.
Yeah, thank you very much, Hal, for inviting me over. And yeah, always I try to find all the excuses to come back to the Bay Area. As I told you, I've been staying here for 4 years and really miss the weather, especially right now. You don't want to go to Indiana right now. Yeah, today my talk will be on this exciting work using large language model for autonomous driving, which is one of the key research focus of our group right now, where my students are looking into all sorts of stuff. But just to lay the background a little bit, why I have been looking into this. Well, at Toyota, I have been actually working on a thing called personalized autonomous driving or personalized automated driving. And the background is we found out that commercially available systems for automated driving, especially for those ADAS systems, they have very limited personalized functionalities. One specific example is the adaptive cruise control. I bet most of you are familiar with this concept here. To give you an example, here is actually a video that I recorded. That was actually on my way to my Purdue interview back in 2022. I was playing around with the adaptive cruise control system on the Toyota Camry. And you can see that I'm following that truck in front of me, and I'm changing the car following settings just to showcase, how these settings can be changed by pressing a button on the steering wheel, right? But one of the concerns or one of the key feedback that we got while working at Toyota from our Toyota and Lexus customers through our dealership is many Toyota and Lexus customers, they complain that this kind of system is not automated. They think, you're claiming it's an advanced feature, but why do I have to still change the settings from time to time? And many people, they actually change the settings multiple times during a single trip. I use ACC very often. I actually use ACC on the Volkswagen Jetta when I just drove from San Francisco airport to here. I changed the car following settings for like 5 times during this 40 minutes trip. Why? There are a lot of factors. Traffic conditions are changing from time to time. When there is no surrounding vehicle versus when there are a lot of vehicle packed, you might want to change the settings. When it's rainy versus when it's cloudy, versus it's foggy, the weather can play a big role here. The road type, whether you are driving in downtown Manhattan versus you are driving in the middle of nowhere, Indiana, you want to change the settings, and also your personal mood when you're driving to work in the morning or you're driving from work to your home. Those are different. So those really lead us to think about whether we can make such things more personalized, so we can take consideration of different humans, their preferences on such a system, and use machine learning and allow this system to behave better. So that's where or when we started to look into this aspect of human autonomy teaming, where how human passengers and drivers can team up with such an autonomous system. And another reason that we look into this is not just for traditional OEMs, their systems, but also for like more advanced systems like Tesla vehicles. My student actually found this online. He searched on Quora, and even for the same system, right? Tesla FSD or autopilot, different people, they have different opinions. Some people consider or complain that's too aggressive, and while the others complain it's too conservative. The exact same system, people have different preferences. And the thing that we figured out is there is a huge need that we want to make the autonomous system to be more personalized, to understand the needs from the human passengers and drivers, and better serve them. It's like when you hop on a Waymo vehicle, you want it to be more like a sporty, or you want it to be more conservatively. How we can do that? So that's how we are talking about this whole research paper where we look into human autonomy teaming, and we're looking at a multi-model approach. By saying that is, we're not just looking at how to take vehicle dynamics. We're getting the vehicle speed, acceleration. We change that, and we learn the humans, their behaviors on that. We also learn how we can utilize in-cabin monitoring using like a camera in the vehicle cabin to capture the gesture, the head pose, the emotion of the human drivers and passengers. And we also look into wearable devices, like you use eye tracking glasses or heart rate using smartwatch or ECG, EEG kind of equipment. Those can also, indicate some of the underlying physical or mental states of a specific human driver or passenger. So you see, we published a lot of papers in those different domains. But the key point of today's talk is about the fourth part, right? This last modality, which is taking audio signal, such as the verbal command directly from the human passenger or driver. We think that's the most intuitive one because humans, they can always express their needs by saying out loud, right? I feel it's too hot in the vehicle. I'm really in a hurry. I really want this to be more sporty or things like that. So that's how we actually publish a lot of papers in this field, and we are investigating how large language model can help with respect to this specific modality. So that's the whole concept. We're still doing the work in all those other domains, but today's talk, we're going to talk about how we leverage large language models to help the human autonomy teaming process on automated vehicle. And the reason why we want to use large language model is because when you have a traditional system, say you are driving a traditional Toyota, or you are driving a traditional Ford vehicle, the existing audio recognition system on a vehicle, they can do a decent job, but they're not really good at understanding all those complex commands or some, the underlying needs of the specific human. Taking this as an example, right? These two drivers or passengers, they are saying the exact same sentence. The rush hour is approaching, but one people might tell this autonomous system that you need to be as quick as possible so we can avoid the traffic, while the other might mean, you need to be as careful as possible because the traffic will be complex. So you can see, one is more aggressive, one is more conservative, but they're saying the same exact words. They are meaning the exact opposite things. So within conventional system, even for like current Apple Siri or Alexa, they are not really good at understanding a simple sentence like that, and also your underlying needs. So that's why we think large language model can help that out. And the way we use that, and we actually listed a lot of logos up there. I actually added the DeepSeek logo only a few weeks ago. But we have pretty much benchmarked all those others, and my students is looking into DeepSeek right now. OpenAI's ChatGPT, Llama by Meta, Gemini by Google, also Q1 by Alibaba, Cloud, and also DeepSeek, and among the others. I think XAI, Elon Musk, they're also going to announce the Grok 3 this week. But the way that we're doing this is we are now replacing any existing module on an automated vehicle. Instead, we are empowering those modules by having this large language model as an additional layer. So we think the strengths of LLMs is it can really understand the interaction between the human and the autonomous system. It can do understanding and reasoning. It only requires 0 or just a few shots of planning, and they can do continuous learning or personalization. And the way we do it, different from many others in our field, is as I said, we run that as an add-on feature. We're not replacing anything. We're not doing any end-to-end large language model thing. And we try to avoid the real-time requirement of such systems so they can verify for safety considerations. So we're adding them as an additional layer, and we can always kick them out whenever we think the output doesn't make sense. When we figure out there is any hallucination from those large models. So I'm going to very quickly go through the first part, the first application, and I'll go focus on the second, the third. The first one is about a data set, a benchmark data set that we come up with where we published this work on CVPR last year, where we propose pretty much the first interactive environment for evaluating large language model based agents.
Sorry,
Sure.
so I had before you get into the details,
Sure.
I just had a quick question.
Sure.
You've been framing this initially as like conservative versus
Mhm.
aggressive driving. Throughout, are we going to be talking about the same, like one axis consideration or from okay.
That's just example.
Perfect.
Yeah.
Okay.
It's an easier way to expand this.
I guess, yeah, mostly I'm just going to be curious as you're going through
Yeah.
how your findings from your LLM work could be translated to an actual vehicle.
Correct. And I will show you, actually, I will show you
Okay,
some demos.
cool.
Because, different humans, it's complex, right? It's not
Yeah, so like for myself, for example, I don't care that much about aggressive versus not
But you care
aggressive,
about other things.
but I care, is it a smooth ride? That's my top
Yeah,
priority.
exactly.
Yeah.
So, but yeah, very quickly going through the first part, we pretty much published the first benchmark data set in the context of large language models for autonomous driving. And it contains a lot of different scenarios, 5,000 scenarios, have highway, data, intersection data. And, we annotate a lot of those things, and it has all those instruction, initial state, go state, and everything. It's based on this so-called highway environment data set. So we build on our work on top of that. And I would not go through all those details. And very briefly on this big figure, so that's how it works. We have developed an API for different researchers to tap on their own algorithm and to benchmark that in this environment, and also to test out different scenarios and different components of an automated vehicle. And specifically for APIs, we have different parts of it, and it can guarantee the safety and can allow all these other researchers to work on this field. Again, this work was published by on CVPR last year, and the source code and all those things are on our GitHub and associated with this paper. But this actually paved the road of our subsequent research in this field, which I would talk about mainly about the real world experiment, because I was a car guy, I worked for Toyota, so a lot of the work that I have been working on, I always think about what's the end goal, how we can deploy that on a real world vehicle. I think that's the key. And the first work that I'm going to talk about, also actually published on ITSC last year in Edmonton, Canada. And we actually won a Best Paper Award thanks to Hal on PRB this year, also this work. And we utilize the vehicles, and we test that on professional proving ground. And the key thing is here is still we are trying to provide personalized driving experience or riding experience for the human passenger. And we consider here the assumption is those vehicles are level 4 vehicles, like Waymo vehicle. You don't have to drive, but you still have your preferences for how they will drive. And then we think, again, this motivation, traditional system, they're not good at understanding the verbal commands. The large language model, they can help that. They can understand the implicit commands. Our system is called Talk to Drive. That's the name that we give to the assistant. But here is how it works from a very high level. Apologies for the library found a little bit unclear, but you pretty much switch on the system by saying commands. It's like you say, "Hey Siri" or "Hey Alexa," and then the system will start to wait for inputs. You provide your human command, I right there. So say I'm late for my meeting, or let's drive faster. And then not just your command I, but we're also taking into consideration the context information C and system message S. So context information might mean your current your route, whether you are going to campus, where are going to a grocery store or something like that, and also the current speed limit and all those other traffic regulation. System message is your current speed, your current position from your OBU, and also from your current vehicle sensors. And then we send all those things to the large language model. And then the large language model will provide program directly for our vehicle ECU to execute, and that's it. So the output of the large language model will be, be some program that can directly consumed by the vehicle ECU. And the green part is the feedback loop. So it's many of you work on control theory. So we also have a feedback loop to provide constant upgrade to the system, to our algorithm. You can switch on system again by saying things like evaluate. And then the system will start to hear from you again. You provide your feedback F right there. Also considering your previous human command I and your other programs, and then we'll send that to the memory module and this historical data. For next time, when you switch on the system, then you will not just consider your real-time input, but will also consider your historical data. So that's the high level explanation of how this will work. And of course, we include all those different things. We use the chain of thought prompting, a very common drill for a large language model. And the key thing is the output of such LMs are codes that can be executed by the ECU. And we have that memory module. So we can consider all those historical interaction between the human and the autonomous system. And a busier diagram here, but basically how it works is probably I'll just point right here. The human provides verbal command. Verbal command will be consumed by the speech recognition system, convert audio to text, and then once the audio is converted to text, we send it to the large language model. The large language model will consider all those other contexts, as I said, weather, traffic rule, traffic condition, then generate codes. So the code will be directly consumed by a planning module of our automated vehicle. And you can also provide feedback and then send to the memory module through the historical data that will be also leveraged when the large language model make any commands, decisions. The key point of this whole graph is, if you think about this green part, all these green modules, it's just a traditional automated vehicle. It has all those traditional stacks, perception, planning, control, the sensors, the actuators. We're not replacing any of them by the modules that we propose. Instead, we add them as more like an add-on feature, and we can always kick it out for a safety purpose, because hallucination by large language model, a lot of times they just provide some random output. As long as we figure that out, we kick it out, we fall back to our traditional automated vehicle stack. So that's a way that we tackle this to guarantee safety. And this is a vehicle that we have and that we test out. And of course, it's a Lexus vehicle because I work for Toyota. And we actually want to work with a company that only have Ford vehicle. And when I joined Purdue, I said it doesn't make sense because I'm working with Toyota. It doesn't make sense for me to use a Ford vehicle to work with Toyota. So we actually pursue with this company called Autonomous Stuff. They retrofit the vehicle, the Lexus vehicle for us, and has all those features, the sensors and everything. I bet many of you are familiar with that. This is the testing ground. Our scenario, we have 3 different scenarios. Starting from the low speed, we have the parking lot scenario. It's actually the football stadium at Purdue, the parking lot near to the football stadium. We have an intersection scenario where the Eagle vehicle needs to do an unprotected left turn. We have a highway scenario where there's another vehicle driving in front of our Eagle vehicle in an aggressive manner. And the vehicle needs to make decision how we can pass that first vehicle in front of us. The parking scenario is, our vehicle is right there, entering the parking lot, big parking lot, and the passenger is going to attend a football game, and the large language model will help this passenger to make decision in terms of where to park. And we have some candidate available slots for large language model to pick based on the requirements or the preferences from this driver or the passenger. The testing ground is in a city also called Columbus by sea, Indiana. It's where this company called Cummins, their headquarters is. And we are using that for our research. I'm gonna play this 5-minute demo video, and I'm going to explain along the way. That basically, you will see this, this view that you have different elements of the experiment. Let's see whether the sound can play.
Command. The game is about to begin. I don't want to be late.
So the first time this passenger said the game is about to begin, I'm going to delay. That's it. You don't have to say anything else. You don't have to say let's park near to that tree behind that vehicle, 10 meters away from us. You just say something simple, and large language model can make reasoning, and then find the spot for you. So this case we use GPT-4. GPT-4 found the parking lot that's closest to the football stadium, and then just allow this decision-making module to make that, to plan a path, and then provide feedback.
So I'm in a hurry. Next time you can park near the exit in order to avoid traffic when I leave.
So this human says, he figured out if I park too close, then it might take me forever after the game is finished, right? So probably next time, let's park near the exit, and then just provide that feedback. Then large language model will take that together with a new input and then make the second decision.
So in that case,
Command.
the knowledge that parking further away, where is the person telling them that I want to park further away
Mhm.
because I want to get out sooner,
Mhm.
or is the LLM that is, or is the prompt I want to be able to get out sooner, and the LLM translates that to.
It can be both. So
Okay.
it can be the human already understand that probably after the game is finished, this person provide feedback. Oh, this time takes me forever to go out, and then large language model will definitely reason that and reason that okay, probably it's because I parked too close to the stadium, or the person can directly tell the large language model that if you park too close, it will take you forever to go out. So next time park near to the exit. I think both case the large language model can reason that and make this more like a mapping relationship between the action it made and the results will come. Yeah. So the second time after the input, this is the reasoning process from GPT-4. The driver is in a hurry to catch the game, but based on the previous feedback, they also want to live faster, so I should park near the exit this time. And then the GPT-4 convert this to a program. So the planning module of our system is running a pure pursuit algorithm, can directly take that as an input and then planning the trajectory to find the specific parking lot that's closest to the exit, and that's it. Again, you don't have to say many things. You don't have to say, let's park to that specific parking lot behind the light pole near to those big trees and 5 meters away from the exit. But just saying something very high level, and it's going to make those reasonings. And you just mentioned, I just noticed that this passenger also provide further evaluation. I'm satisfied with this trip. So this will be recorded for this specific passenger for his future human autonomy teaming process. So it means, and I work on digital twin. It means digital twin is built for this specific human passenger at this specific scenario. The second scenario is the intersection scenario. As I said, the unprotected left turn. And he says something like, command, I'm on my way to the emergency. So it shows a sense of urgency. And then GPT-4 in this case, reason that the driver is in an emergency situation, so I need to go as fast as possible while ensuring safety. And of course, our vehicle is still constantly checking the surroundings. This is our LiDAR map, bird eye view map, and calculating time to collision and everything. Actually decided to turn left before the other vehicle passed, while guarantee all the safety features already, guarantee. But still, this passenger was not happy, and he provided further feedback. After it's down, even though sometimes in a hurry, next time you should still wait for the opposite vehicle to pass. So provide that feedback, showcase that he's still that kind of conservative passenger. He really values safety. And the second trip, consider all that, have a new input. I'll be late for meetings. Again, very implicit, very high level. But this time, the GPT-4 reason the driver is in a hurry, but also concerned about safety. We need to speed up, but also wait for the opposite vehicle to pass. So this time, it sends input to the motion planner, and motion planner decided to actually go there, decelerate, stop, using the perception module to constantly check the surroundings using a LiDAR. After guarantees the vehicle already clears one intersection, make another decision. And also the vehicle, the passenger still provide feedback. Let's continue turning when it's clear, and then this time the vehicle turn after it's all cleared out. And he can still provide constant evaluation. This time he said afterwards, I'm satisfied with the trip. So again, the digital twin is built for the human autonomy process for this specific human passenger at this specific scenario. The highway scenario is what we encounter every day, while we have always like aggressive driver driving in front of us, doing like a zigzag driving or sometimes just cut you off. And command the front vehicle looks very weird. That's it. You don't have to say, let's overtake that vehicle or let's change the speed to something and go right or something. The driver thinks the behavior of the front vehicle is unpredictable. To ensure safety, I should change lanes and slow down the speed. So that's a decision by GPT-4. He was not happy. Next time, please directly overtake the front vehicle. Provide this feedback. The feedback will be captured by the memory module, be concatenated to the new input. So next time, the new input, high level again, the front vehicle looks very crazy. And then this time, considering this input together with the previous interaction, the driver's previous feedback indicated a preference for overtaking rather than just changing lanes. So clear overtake, and that's it. I do want to mention those numbers on this window. So you can actually see some numbers, although a little bit small. 4.91 seconds. That's the time it takes for the audio to get transferred into text. Because even these people, he said that sentence, it takes like 2 seconds. And it takes another 2 or 3 seconds to transfer that into audio to text. Nothing related to large language model. This part is actually the communication time, processing local content and send that information to the cloud, because we're using OpenAI's API on the cloud. This 1 second is actually the reasoning time of GPT-4 large language model. And this is the actuation time by the vehicle controller and designer. So, but if you combine all this together, it can be a large number, like 6 seconds. So you can now rely on such a system that every time your output will be generated after 6 seconds, you describe a thing. So that's why we think this kind of application will be very useful for high-level decision making, for high-level preference setting for a specific automated vehicle, but not for a very safety critical or time critical application. So that leads to our next work after showing the results very briefly. We of course test out all those safety metrics, comfort metrics, efficiency metrics, showcasing that our large language model can guarantee all that, and also the key index, the key metrics that we value our system is the takeover rate. And I know level 4, level 5 vehicles, there's no takeover per se, but even for a Waymo vehicle, you can at least like press the emergency button or help button. We consider that as a takeover, which means this human passenger is not happy about what's going on. But when you have this large language model driven system, they are more happy about everything. They trust the system more. They take over less. So that's how we build on trust between this human and autonomous system, and help this human autonomous process. And I do mention those limitations for this work. We rely on the cloud. And there's network dependency issues when you're driving, as I said, middle of nowhere, Indiana. You don't have communication, so there's no way you can run GPT-4 or GPT-4o on the cloud. And also, if you use vision, large vision language model, when you have vision part of the things get included, that's actually introduced even higher latency. Just for the model itself, it takes 3 to 4 seconds response time. And also, I talk about this memory module. Every time you concatenate the new input with the old input, but when you have thousands of interactions, and that's going to be a long text for your large language model to consume every time. And some users, or in this case, our students who test out this system, They still complain that the behavior is not really good for everyone, even if they have a large language model. And some difficulties in understanding context information and everything. So that's why one of our latest work, where it's still under review by CVPR this year, is we're looking into some workaround. We want to do things actually everything on board. And that's actually how Toyota likes it, because I think car companies, they don't want to rely on third party. They don't want to rely on some other companies. They want to have everything on board. And we also have vision part included. So it's actually a VLM. It's not just a LLM, but we're taking vision part in part of this. Probably I'll go through all this motivation very quickly. We talk about the latency. We talk about the limitation of large language model. So that's why we want to have also the perception module kicks in and allow us to make more informed scene understanding. Another busy diagram showcasing how this works. But essentially, we use vision language model for motion control. In this case, we have MPC algorithm for lateral control. We have PID algorithm for longitudinal control, so car following, lane keeping. And for each algorithm, we have 3 parameters to tune. So for PID, of course, KT, KD. For MPC, we have 3 defined parameters. The thing that we're trying to solve here is we want to use all those other things that we said earlier, system message, human instruction, memory module, but also the camera image. They are all as inputs to our vision language model. And this vision language model is actually deployed on board, on the vehicle, not on the cloud. And then based on those inputs, we then fine tune the parameters of those 2 algorithms. We send them to the vehicle execution, and then just to update the way that the vehicle drives. So also a very simple idea. Again, very similar inputs. The only new thing is the vision input. Here we use the Q1 model from Alibaba, from China, a lightweight 8 billion model. So it's just 20% of the parameters that we have compared to GPT-4 model that we run previously, the 40 billion model. So it's more lightweighted. And the outputs are matrices for MPC and PID algorithms. And we also leverage this RAG based memory module retrieval augmented generation, for those of you who are familiar with this concept for personalized motion control. And some further details, we actually fine tune this specific Q1 model. We use 4 NVIDIA A100 GPUs that our lab has access to. So it takes 5 hours. It doesn't take forever. So in total, like 40 hours for one single GPU. And for each training set, take 5 epoch based on this new scenes data set that we use. But besides that, we also build our own data set. I keep talking about extreme weather in Indiana or Midwest. So yeah, we have all those different things. I think you guys also have this, but not snowy weather, foggy weather. San Francisco has it a lot. But this actually plays a big role, especially when you try to deploy such a system in such a weather that will really affect the way that your vehicle is behaving. So we have all those different data sets. Also keep fine tuning this Q1 VLM. And we also have another demo video, but I'm just gonna show the second scenario, the very small part of it, because this is still ongoing, on review. Again, we use vision language model for fine tuning the controller of the system. Very similar command, I feel a little bit motion sick. So it's actually the second trip. The first trip, there's nothing. Input from the passenger. This time he said, I feel a little bit motion sick. We actually compare the system, a little bit low resolution of the video. We actually compare the system with the previous setting. The previous setting is the passenger didn't say anything. This time, he said he's a little bit motion sick. So actually you can see the longitudinal velocity and lateral velocity is less aggressive. Or you consider the longitudinal acceleration and lateral acceleration are smaller, because we want to drive in a more conservative manner. So over time, the parameters they are tuned based on the vision language model, and then to allow this human to say to feel more comfortable, but he still think it's still aggressive. Provide a further input, please drive more gently, right? And then the trick after that, considering this input again, having the vision language model as the processor will further make the diagrams even more like smoother, right? To make the longitudinal velocity, lateral velocity to change over time, like in a more milder manner. Let's just say this one goes up in a slower fashion. This one, the perturbation is even smaller for lateral acceleration. And it's of course considering the vision input for the image and also the surroundings and everything. So trying to make the driving behavior to meet the preference of the specific human passenger. So that's what we do. And very quickly, on a particular question that I got asked a lot of times, what if the output of such a system doesn't make sense? What if the output is totally wrong? Then our take on that is we always have a safety filter, keep monitoring the output of our vision language model or large language model. Whenever the safety filter falls out of bound, like the output falls out of bound, we'll just kick it out. We'll just fall back to our existing module. We have our existing, computer vision algorithm for perception, our A-star algorithm for planning, for example, PID algorithm for control. So that's always doable. It's not like an end-to-end system that you rely 100% on such a black box. So that's our approach for this. But we are still doing a lot of work ongoing. We showcase the performance, different metrics. That's how we value the system and everything. And again, the takeover rate is reduced from what we claimed, which means the human autonomy process is more trusted. We build more trust for this human on such an autonomous system based on this modality of input, audio. And if we build this on top of the in-cabin sensing on the wearable devices, as well as the vehicle dynamics, and that's a whole story that we are trying to build for a human digital twin on human autonomous system teaming process. So those are some of the work, and of course we get actually advertised by some media, and this one actually is from Bay Area, from what I noticed.
Researchers are working on the next level of driverless cars that can take commands from passengers who are on board. And the researchers from Purdue University in Indiana are pairing AI models like ChatGPT with the driverless cars.
One driver see another driver
That's our parking lot, football stadium,
so
and
just tell the large language model, say, hey.
I think that was the routers there. Not the Associated Press. They're here to give a press release on this research. But we actually showcase that this whole system can work not just in our video, but every time we have external guests, it can work out. Because a lot of times, when every time we have VIPs, the demo will not work out. But we managed to make it work out every time. And lastly, it's all by my students. And actually, this is a group photo. Two announcements I always made. First, that's not my student. That's Jeff Dean, as many of you know, the chief scientist of Google. He actually visited us. He tested our system. He asked this very critical question: why GPT? Why not Gemini on your vehicle? And we say, we test out actually Gemini because he's actually the people behind Google's Gemini. And just at that time, Gemini was not performing very well compared to GPT-4, but the new Gemini system, we benchmarked it and it works very well. Second announcement, this student was not injured by LMs, he was injured by playing soccer, so nothing to do with this large language model. He's actually the passenger on those videos, so he's the main driver, Kan Kui, that just happened to be. He got injured, and Jeff Dean is visiting, so he wants to join us to take that photo. But so basically, he's right now interning at Toyota in Bay Area. These two folks, they are going to intern at Waymo Research this summer. So they are really bringing all the state of the arts from industry and then continue to build our research. And our funding is coming from Toyota, from Bosch, Hardware Foundation is also providing a lot of computational resources, but major funds from USDOT, specifically the Center for Connected Automated Transportation, which is led by University of Michigan, Professor Henry Liu. But with that, thank you very much.
We had
Now the head of Umtree.
Yeah.
we did have a question in the chat. Joshua Mung was asking, have you considered small language model since driving tasks only involve specific knowledge?
Yeah. I think I noticed that question comes from the first part of the research, and I think I already explained the second part of the research. We are actually doing small language model. We're not doing large model anymore. It's a smaller model. It's specifically for driving context. So we don't have to worry about all those other contexts. We don't have to get a very heavy model. But yes, that's our focus. We have small model. We want to deploy that on board.
Then,
Good question. Thank you. I like the part where you mentioned latency issues because I know the LLM had that issue. So I think that part is true. And one thing that I had was you played a video of the guy that like wasn't that happy with the outcome. And my question to you is like, how do you address different personalities and different behaviors and different directions that people will give to the LLM? I'm sure there's biases and certain different characteristics. So how does it address like which one is the best behavior?
Well, there's no best and there's no worst. And the way that we want to do this is want to satisfy their needs as much as possible under the certain threshold. So say I'm very aggressive. I ask my assistant, let's drive 200 miles per hour, which is not feasible, right? But I would just cap it under say 80 miles per hour. But I'm trying to satisfy your needs as much as possible versus others. Let's drive as slow as possible. I feel very uncomfortable, but you have to still follow the traffic flow and everything. So that's why we have all those surrounding information, the context information. Those are all input. So it's not just one single input from the human, but we still consider all those others and then make the most reasonable decision for your vehicle.
I'm curious, what if a user were to say before they get into the vehicle that they prefer a safe driving scenario, but then in the actual vehicle themselves, they say, okay, go 60 miles per hour off the start. I'm curious how it would assess that.
So we put on different weights on the historical data and the real-time data. So yes, when you say something new, we always put more weight on the newer inputs. But as I said, we concatenate all your historical interaction. We still consider, although you are preferring, more aggressive driving, but you still probably have a sense of safe driving. So it's just a matter of how we put on weights on that, and then how we can satisfy your needs based on the inputs that you have.
Yeah, thank you. That's a great talk. It's very
Thank
interesting.
you.
I have two questions.
Sure.
One is that, so let's say you have already tuned this language model system for one type of autonomous vehicle, and now you want to migrate it to another autonomous vehicle. Maybe the driving, like the software systems and all that is different. Like how much fine tune do you need to do this?
Yeah, so that's actually a question that we haven't thought about yet because we only have that one single vehicle to test out. But going back to my Toyota time, we are trying to provide personalized autonomous driving for different Toyota and Lexus vehicles, and different vehicles that have different software and hardware features, right? We're talking about a Toyota Sequoia, which is a Toyota Supra, totally different objects. So the amount of work, I don't have a number for that, but it might be significant because a lot of times you might rebuild the whole thing from scratch. That's the way that the vehicles drive, probably an EV versus say ICE vehicle. These are totally different. But our motivation is try to make this as scalable as possible. We can try to make this generic, only focus on the human object, make the autonomous system less important factor, but focus more on the human input and focus more on the human object and try to make these things more scalable. Because otherwise, if this is only doable for you driving on this Lexus RX, but not on another vehicle, that doesn't make sense.
I see. Yeah. I have a second question is, so do you see the potential of these type of tools to be extended to vehicle or vehicle to infrastructure communication?
That's what one of my students is doing right now. And that's actually my previous research focus, cockpit drive automation, as Kyle just introduced. But we think there are uncertainties out there. When you introduce another layer of communication. Because even for now, if you're using large language model on the cloud, you already have your vehicle talk to the cloud talk to your vehicle, and you are relying on this vehicle talk to another vehicle, and that vehicle has to talk to the vehicle. The communication overhead can be very large. And also there are way too many uncertainties. You are bringing new vehicle and their behavior might be hard to predict. So one last comment on this. I actually talked with Waymo folks like many years ago, 2018. I asked them, why didn't you guys start to work on V2X? Why do you just focus on single agent automation? And I asked this question again in December when I visited them again. They said, even for a single vehicle automation, we still have a lot of different unsolved research challenges, right? All those long tail cases and stuff. If we're introducing yet another modality of data communication into that, it's going to be making this whole thing a mess. So we're focusing on address this thing first until we decide to move forward. So yeah.
And also when you have this outside communication, like language model logic is also different, right? It becomes like a group chat.
Correct. Correct. Yeah, I was actually trying to ask my student to, use one large language model on one vehicle and another large language model on another vehicle and allow large language model to talk to each other. That's my quick thoughts. And this is not making sense. You can simply just use one model, capture data from others, and just run that. Because you have one LM talk to another. Who knows what they ended up with, right?
So there's another question in the chat from Peggy. She asked, she said, thank you for sharing the research. I have two questions. The first is how the trust is evaluated.
The trust is evaluated, right? So Peggy, the trust, as I mentioned, the key metrics is the takeover rate. And here, because it's a level 4 vehicle, the takeover rate is simply if this passenger, in this case my student, was not happy about what's going on, driven by a large language model, he will simply press the brake pedal on the vehicle, which showcases, okay, I'm quick, I don't like this, and I will probably stop all the things, and that's considered as a takeover. And our conclusion is that with large language model or vision language model, such behaviors, such scenarios would be much fewer compared to without. So by trust is evaluated by the takeover rate.
And then the second question is, what is the benefit of your approach comparing with categorizing the driving style into a handful number of styles such as chill, standard, hurry, like Tesla does, and let the user select what they want from this?
Yeah, that's a good point, and that's exactly what James was asking about, right? Because we think human beings are complex, right? It's not just a simple matrix that we can describe that. And even for myself, when I drive to Purdue in the morning versus when I drive from Purdue to home, it's totally different mindsets, right? After the work, I'm more chill. In the morning, I'm more in a hurry. But I don't want to change the settings every time. I want this to be more intuitive, to understand all my needs. So that's why we think there is a need. There is indeed a need if we want to build a more complex, more fine-tuned, autonomous system for the future. But right now, it seems like, Tesla's approach, they have a handful of features, they work very well. But probably some drivers, they still complain. They don't truly understand me in all those different contexts. So, yeah. Thank you.
Thank you.
Thank you, Peggy.
Is your test vehicle an EV or?
It's actually a ICE tradition. It's a 2019 Lexus, so it's a hybrid. It's a hybrid, but it's not plug-in hybrid. So it's just a hybrid vehicle.
So when you tune the control parameters for this ICE vehicle automatically, did you still consider like stability of the controller?
Yeah, we didn't go into that deep because actually autonomous stuff, this company, they already have a baseline model for PID and MPCI within. And that's actually on the AutoWare. AutoWare is a layer based on ROS. So yeah, it's complicated. Autonomous stuff is a company who provides this whole vehicle to us. And then we have a lowest layer to interact with this vehicle is ROS, robotic operating system. And AutoWare is built on ROS. That's more like autonomous system, autonomous driving architecture. And so we can use AutoWare to integrate our annual bar algorithm. But we don't go into the lowest layer that you directly look into the combustion and of the vehicle.
I was wondering if you're considering using large language models in any other type of human to vehicle interaction, because ultimately I feel as though the extent to which you can personalize driving while remaining within safety constraints is rather limited.
Yes.
And so, but I see great value in this, but the value I see in this is from what you were speaking of, like the human and vehicle interaction. So I'm wondering, are you considering it for any sort of like vehicle to passenger feedback?
Yes.
Because you had in one of your flow charts, you had human feedback. So something I noticed was that there wasn't any vehicle feedback to the human. And ultimately, the way I envisioned this, and this is, shaped by pop culture in many ways, is how, the Star Trek computer, the computer in the Enterprise in Star Trek, where the passengers in the starship were interacting with the vehicle in conversational terms. And it was not only directing the vehicle, these commands, but also receiving information back from the vehicle, depending on operations. So I'm wondering what other ways you're considering using large language models in AV development beyond just personalization of driving.
This is of immediate interest of the car company to it. So of course, they evaluate that it's more important to have a system that can work best for their customers. But I think you mentioned vehicle to pedestrian interaction, or passenger or pedestrian?
Either.
Yeah. Pedestrian, I'm not sure if any of you still remember, many years ago, there's a company called Drive by AI. It's actually by Andrew Wang from Stanford University. Their vehicle actually have a kind of a LED in front of their vehicle for interaction with pedestrians. So, the vehicle will showcase, okay, I'm not in a hurry, you pass first, that kind of thing. So that kind of interaction, I think it will be empowered by a large language model. If you have, or vision language model, you have a vehicle that understand what's going on, understand, okay, whether you're going to cross or whether you're not, reason on that, and showcase that output to the human pedestrian. So the pedestrian will know, okay, that's your reasoning process. So that's what you want to do. It's safe for me to cross or it's not. So that can be another object. And a few of my students are exploring all those other domains of this. But I think the key thing that we are still focusing on is what's happening inside the vehicle in terms of more like driving, because that's of the immediate interest of our sponsors and also our collaborators. But yeah, there are a lot of options.
This is a broader question, so
Sure.
Please forgive me for not being very precise. I'm curious if you have done already or are planning to do work on how requests for people for autonomous driving, more specifically level 3+, where the human will not actually have to have full-time responsibility and will be free to do from other things, how those requests may differ from the typical driver request, especially in a classic driver assist technology where the driver still is in control. It's just more of a, say, I don't want to be so close to tailgating. So, for example, you can envision there might be very different requests that I would put in for an automated vehicle if I wasn't driving. It might be, oh, I have a meeting for an hour, so I'm going to tell it, please pick a route that please pick a route that will get me there exactly an hour on time, and I want it to be very smooth. Or if I have a child in the seat, I might say, please bounce up and down a little bit because he likes it being bumpy. I'm also curious if you guys have explored that and if that's of any interest towards Toyota, because that does seem to me one of the big gaps. Like, we talked about Waymo vehicles and the like on prioritizing comfort, but it doesn't seem like it's really in the objective function as much. It's more, we need it to be safe and we'll try to be relatively smooth, but that's it. I'm just curious if you've explored that of like what people actually want out of a driving experience of an automated vehicle that would be different from what they want if they're driving a vehicle.
I think there are many different things that's going to be empowered by this. And to tell the fact, I think at least I know a lot of OEMs, especially in China, like
I'm thinking of China. Yeah, China's honestly ahead of this stuff.
They like Xiaomi and NIO and all those ones. they already implement large language model on their vehicle. That's already the case. I think the latest thing that my wife actually shared with me, she's nothing to do with this. She shared with me that Huawei or any other brand, they already implement DeepSeek on their vehicle.
Yeah, and there was like the article in the Times this morning. It's like, oh yeah, Porsche is in luxury in China because it doesn't have all of these fun features that all of the Chinese vehicles.
Yeah, and it's like 5 more times expensive.
Well, yeah, that's so.
But a lot of OEMs, they are really looking to this. They're doing large, LLMs or foundation models for their smart cabin.
Yeah.
A lot of those different features, probably the one that you just talked about, that can be a smart cabin kind of feature.
Yeah.
The only thing that for us is a lot of things that we think that are cool, they don't have that much research value. It's more like implementation kind of thing. So my students, they want to publish the VPR paper. So they always want to look at, well, what's hot out there, perception and everything.
Yeah.
I have a lot of cool ideas, but it's hard to persuade them to, put time on that and work on that. But yes, I think there are a lot of possibility to work on, especially if you work with industry partners. They might have a lot of needs for that.
I would argue that actually does have where you're going to find the academic interest is more going to be, I would say, probably on the planning side and the like, from how people are going to be perceiving and using the vehicle. So like these are a bunch of open questions, like let's say in the planning literature, what is going to be the value of time of somebody in an automated vehicle? And people for the last 15 years are basically throwing darts at a board to guess what that is going to be. This kind of work. So like I would, it's probably not your type of engineering work, but there is academic interest in these sorts of questions.
Back at Toyota.
Sorry.
Yeah, we work actually at the digital twin kind of thing. There is a huge research pillar. It's called personalized recommendation, and that's exactly about the story that in the future they're all like Waymo level 4 level 5 vehicles. What all those different passengers will end up doing on a vehicle, whether they want to watch movie, whether they want to take a rest, whether they want to play cards with others and things like that. How we can provide recommendations in a personalized manner. So we actually add to it. I think they're still working with a professor in UCSD, computer science, working on recommendation algorithms, trying to sort of those out. It's more like a Netflix, Amazon kind of thing. It's not anything to do with driving. So that can be directly benefited by a large language model, I can imagine. But it's outside of my domain. So that's why I'm not. Yeah.
We are over time.
Okay.
So thank you so much.
Thank you for organizing all this. Thank you very much. Thank you for watching.